All right, so I want to take a little bit of a detour, and I know that in our previous lecture we looked at, when making alkynes, this was kind of a little side thing to watch out for because these terminal alkynes are slightly acidic and can be deprotonated with a strong enough base. And I kind of made it sound like, oh, that's kind of a detriment. We wouldn't get the product we want. But what I'm going to do is turn this, what we call a satellite ion, into a benefit and look at one of our first instances of doing a carbon-carbon bond formation. So again, just to review, if we take a terminal alkyne, has to be terminal because it has a hydrogen on it, and use a strong base, that hydrogen gets deprotonated and we make what's called an acetylide ion. Now, I want you to take a look at that. You got a carbon with a negative charge. All right, think about that for a second. I'll come back to that. Now, we can't use bases like hydroxide or alkoxide bases. They're not strong enough to do this deprotonation. So the most common bases that can do this, that I want you to know, we can use sodium amide, or we could use sodium hydride, or we could use something that's known as LDA. LDA stands for lithium diisopropyl amide. Yep, so you got N with a couple isopropyl groups, a negative charge, and then a lithium counterion. So just kind of memorize those three. There are strong bases that can be substituted for that, but those are the three most common ones we'll use in a lab to do this. Now, why do we care about making acetylide ions? I'm going to go back to the question I asked you earlier. What is special about having a carbon with a negative charge? It's a really good nucleophile. So let's think about that. If I have an acetylide ion and I react it with something that's got a leaving group, like an alkyl halide, I can just do an SN2 and look at what I'm making here. Let's number these. 1, 2, 3, 4, 5. I am drawing a mechanism here that is going to connect carbon number 3 to carbon number 4. And this is the first instance we've seen of making a new carbon-carbon bond. There's 1, 2, 3, 4, and 5. So that bond between 3 and 4 is a new carbon-carbon bond. I say this half jokingly, but half serious, actually more serious. But if you want to win a Nobel Prize in chemistry, figure out a new way to make a carbon-carbon bond. Because that's such an important tactic when it comes to multi-step synthesis. This is a way, one tactic that we can use now to take small molecules and make big ones out of them. It's like connecting two pieces of a puzzle together. We take two small puzzle pieces, we put them together, and now we have a bigger piece. And we can keep on adding to that. And so carbon-carbon bond formation is huge when it comes to synthesis in organic chemistry. So this is a very, very important reaction. In fact, put that somewhere in the margin of your notes. Like you're going to use this to increase the chain, the amount of carbons in a carbon chain. Now, I do want to highlight an important side note. We can only use methyl halides or primary halides. And here's why. So if we use a methyl halide, the only thing that can happen is substitution. So there I just added one carbon to that acetylide ion. And then in the previous example, we reacted this with a primary alkyl halide. Now, one of the downsides to this being such a great nucleophile, the acetylide ion being a good nucleophile, is it's also a very strong base. And so if you have a secondary leaving group, it's not going to do substitution. What do you think it's going to do instead? It's going to do elimination. And so the acetylide ion acts as a base instead of a nucleophile, and we get elimination. So that's why we can only use methyl halides or primary halides to do this kind of carbon-carbon bond formation. So let's kind of look at a few examples because I really want to hammer this point. One of the cool things about using acetylene is acetylene's got two terminal hydrogens. So I could add a group here if I wanted to, and a group on the other side. I can't do it at the same time. I have to do one, put one group on first and then put the second group on. So the process to do this, let's say, for example, let me back up a little bit. Let's say this was our target. We want to make this. I see my triple bond there. And if I start with acetylene, that's where my triple bond is going to come from. And I'm basically going to replace the hydrogens on both sides of acetylene with these carbon groups. I got a 2-carbon group over here, and I have a 3-carbon group over here. Oh, that doesn't look too good. There. So what is my tactic to putting these on? Well, I put one group on first, and usually it does not matter which group I put on first. So my tactic is step 1, deprotonate, use a strong base, and then step 2, add my first group. I'll put the 2-carbon group on first. And so the base will deprotonate the hydrogen. That acetylide ion will then react with the alkyl halide, and I put my 2-carbon group on first. Again, it doesn't matter which one you put on first. You just have to do them separately. You can't just say, oh, I'm going to throw a whole bunch of base in, throw all my alkyl halides in, because then you're going to get a whole bunch of unwanted side reactions. And again, just to remind you, the number 1 and the number 2 above the reaction arrow, super important. You cannot forget those. If you don't put those, you are saying, I am mixing the base and this alkyl halide together, and that will lead to eliminations. So then I'll do this again. Throw in a strong base. So use sodium amine ammonia. Again, you can use any of these 3 bases here to accomplish this. And I'm going to throw in my other group. So I want 3 carbons, 1, 2, 3. So that's the other group I'm putting on. And so now step 1, that base will deprotonate the other terminal hydrogen to make an acetylide ion. That in turn does an SN2 on the alkyl halide. And now I have both of my carbon groups on around that triple bond. All right, so right now, make this easy on yourself and really master it and kind of look at this as this is the only tool in my toolbox that I have right now that I can extend the chain of a set of carbons. How do I do that? I need to start with a terminal alkyne. So when you see a problem, like for example, this, Don't freeze up and say, I don't know any reactions that will do this in one step. Yeah, because we don't. We don't know any reactions that will do this. But if you look at this and say, well, if I have three carbons here and I'm adding two more, what do I need in order to extend the number of carbons on a carbon chain? Well, I need a terminal alkyne. So maybe one of the steps in this process is I'm going to start with an alkyne. Those are my two carbons there. And if I add a strong base, actually, I'll switch it up. Let's use sodium hydride. And an alkyl halide, notice that's where those three carbons that come in. I now have my five carbon chain. And you might look at that and say, well, that's an alkyne. How do I get to an alkane? Well, this is where our next video will come in. We're going to look at reduction processes that, again, we did reduction in the alkene chapter, adding hydrogen across the double bond. But we're going to do some other really cool stuff with it because we have two pi bonds. We don't necessarily have to reduce it to an alkane if we don't want to. We could stop at an alkene. So we're going to look at that in our next video.